How does a fire spread in and around buildings? Let's have a look. Well, first of all, fire spread is exponential. What does that mean? Well, it's a chemical reaction. What it means is, after double the time, the fire will not be double the size, it will be 4 times the size. After 3 times the size, 3 times the time, it will not be 3 times as big, it will be 9 times as big. That's what exponential means. Now, fire can spread in 4 ways. There's 4 ways a fire can spread. Firstly, you've got conduction, convection, radiation, and direct burning. Let's go through convection first then. This is the most common cause of fire spreading buildings, convection, hot air rise, the most common cause. Now, it can only occur in gases and liquids, not solids, so solids can't have convection. Convection is the main cause of it, and it's due to the fact that hot air is less dense than cold air. Because did you know that air weighs something? Now, just to be a favour, just put your hands like that. Put your hands like that. And can you feel the air in your hands? Does it feel heavy? People do that and they say, it's hard to tell, I think that's my hands. Air does weigh something. If you went outside now and got all the air from 1 square kilometre, all that air, brought it in a room and compressed it all, how much would it weigh? How much do you think the air would weigh? People say, I don't know, not a lot, not a lot, not a lot. Well, I'll tell you how much it'll weigh. 10 million tonnes. Air possesses mass. Did you know that 1 metre cubed of air at ambient temperatures, 1 metre cubed of air, that bit of air, weighs 1.2 kilo. That is the density of air. 1.2 kilo per metre cube. That's the same as half a bag of sugar. Half a bag of sugar. Now, what happens if you heat air? So the fire heats the air. Well, it expands. Well, if it's expanding, what's happening to the density? It's being reduced. It's becoming lighter, less dense. That's why hot air rises, because the air is less dense. Hot air is less dense than cold air, and it rises. Now, did you know that all gases expand at the same rate? All gases expand by 1/273rd of its volume at 0 degrees C. So, if you increase the temperature of a gas by 273 degrees than what it was at 0, what's the density? Well, it's halved. What temperatures do you get in fires? 600 degrees is flashover. You can get temperatures of 1,000 degrees. Well, if you heat air up to 1,000 degrees, it's now about 1/4 of its density that it was at 0 degrees. So convection is due to hot air being heated, rising, less dense, and as it travels away, it starts to cool and it starts to come back down again. That is why you normally see the pattern hot air rising, convection. In a fire, the convection currents can carry hot gases upwards through stairwells, open shafts, and it spreads the fire by taking embers as well. When reaching the ceiling height, it spreads laterally, it starts to go away. And what happens? Basically, how do you prevent fire spread due to convection? Well, you compartment buildings. Compartmentation. You can use fire separation. Fire stopping openings. Don't let the fire get through openings. You can use fire-resisting doors. And finally, fire-resistant walls. So that covers convection. So don't forget, convection is hot air rising due to being less dense than cold air. As it travels away, it's heated. It's replaced by cold air, which gets heated, and that travels up. And as it travels away, the air loses its heat and it starts to come down. The next mode of heat transfer I'm going to cover is radiation. Now, radiation is the main cause of external fire spread. Not internal, external fire spread. And it can be described as electromagnetic heat transfer, and it's basically infrared radiation. It travels in straight lines. Radiated heat travels in straight lines. Now, do you think radiation can travel through a vacuum? Well, what heat do we get from the sun? Radiated heat. It's travelling through a vacuum. Yes, you can. Now, fires caused by radiation can travel through a glass window. Can travel through a glass window and spread fires. So that's why if you wanted to build a building, that's why there's boundary distance in buildings. Buildings are not allowed to be built too close to the building because of radiation. Radiation was the main cause of fire spread in the Great Fire of London. That's why the boundary distances came in. Because there's a fire in London at the time, the houses were too close together. There was a fire on one side of the street, the radiated heat travelled across the road and it spread the fire. Did you also know that the intensity of radiation in a fire is inversely proportional to the square of the distance? Did you know that? What does that mean? Inversely proportional. What it means is, if you half the distance, it's 4 times the intensity. If you've got a fire and there's a cylinder being heating the fire 5 metres away, and it's 1 unit of heat at 5 metres, what would the radiation intensity be 1 metre from that fire? So at 5 metres it's 1 unit, what's it at 1 metre? What you do is you flip it over, it's a fifth of the distance, flip it over, which gives you 5 over 1, and you square it, 5 times 5, 25 times the intensity of radiation. Do you understand why these distances, where you should store skips away from buildings, get them away? Because that's the principle. If you put things too close, the radiated heat is massively intensified, and that's the main cause of external fire spread. How do you stop fire spreading from radiation? Well, physical space separation. Get them away. How far should you store ignition sources from cylinders? As far away as you can. And if you can't, you use physical barriers. So you put a physical barrier there instead. Fire brigades, when they turn up, how do they protect cylinders in a fire due to radiated heat? We put spray jets on, with sprays on to protect. The next heat transfer mechanism I'm going to go through is conduction. So I've covered radiation and convection, now conduction. Conduction is the transfer of thermal energy between neighbouring molecules in a substance due to there being a temperature gradient there. And it always takes place from a region of higher temperature to a lower one. It's always transferring from higher to lower. And it acts to equalise. Let's say now I've got a metal bar in my hand, yeah? Now that metal bar, if you looked at those molecules in a microscope, they have all got kinetic energy. They've all got... Those molecules have got kinetic energy and they are vibrating. You can't see it, but that molecule is vibrating. And that's at normal temperatures. If you heat that bar up at one end, what happens to the kinetic energy of the molecules at that end? Well, it increases. So the molecules at this end are going like this. And the molecules at this end are going like this. Now, good conductors will allow the kinetic energy of those molecules, that heat to travel down them. So that's what conduction is. It's the kinetic energy molecules. A good conductor will allow it to travel down until it equalises and the bar becomes the same temperature. And that's how fires used to spread, due to conduction. You've got a metal bar going through, a metal beam going through a building with a compartment wall in. If there's no fire stopping, the heat will travel straight across the fire. That is what conduction is. And it can be relevant to solids, liquids and gases. Again, like I said, if you hold a metal bar, that's what happens. Good conductors are metals, so silver and copper, for example. Poor conductors, wood, cork, glass, asbestos. So if I've got a lump of wood, the molecules are vibrating. If I heat up one end, what happens to the molecules at that end? They vibrate more. But poor conductors will not allow that transfer down the wood. Think of a steel door, that's why you fill a door for heat, don't you? Due to conduction. How do you prevent fire spreading from conduction then? Well, for example, a steel girder across the compartment wall must fire stop it. So basically you put something in between that's a poor conductor to stop the heat travelling across. You can insulate structural steel with fire resistant materials to stop the heat getting to it. Originally they used to do it with asbestos, but we know the problems with asbestos. Now they use spray mineral coatings and dry linings. The last heat transfer mechanism I'm going to cover is direct flame impingement, which actually is a consideration of the other three. So basically, direct flame impingement, in a way, is the flame directly touching it, is a combination of all the other three. Let's just summarise fire development. I come in here and I set fire to a chair. As you set fire to a chair, what's the first mode of heat transfer? Up. Hot air rises due to convection. The hot air is expanding, it's rising. That's convection. When the hot air reaches the ceiling, if there's a metal floor and you're stood above it in bare feet, what will happen? Well, the heat's going to travel through the metal due to conduction. So the person above it will go in, my feet, my feet. Now, as the heat travels across the room, what heat's coming down? Radiation. So as the hot air travels across, you'll get radiated heat being travelled across. Now, as the hot gases heats the radiation, what happens as more gases come across and it starts to go down and down and down? What happens to the intensity of radiation on that table, for example? Inversely proportional to the square of the distance. Can you appreciate, as it's getting lower and lower and lower, the radiated heat is travelling down, it's getting much more intense, those materials start to decompose, pyrolyse and give off vapours. Eventually there comes a point when the whole room goes up, and then you've got the whole room involvement, which basically is a flashover. And that's what I'm going to cover later on.